I hope it's recording now. Okay. Hi everyone. I'm sorry I tried to record a few times, it didn't work out. So my name is Deborshee. I'm a postdoc at Duke University and also at SAMC, which is the Statistical and Applied Mathematical Sciences Institute. I'm going to be talking about efficiency of sampling for stochastic gradient MCMC for hidden Markov models. This is joined with Rihui, who is at Duke, he's a graduate student, Alex, who is a faculty at Harvard, he was earlier a postdoc at Duke, and David Dunson, who's my mentor here at Duke. Okay. I'll jump right into it. So hidden Markov models consists of observations yt indexed by time, and the way these are generated as follows. We assume that there is a latent Markov chain xt, which we don't know that, the Markov chain has state space omega x. In this work, we assume that the state space is 1 to k, so it's a hidden Markov model with what's known as a discrete state space. This is the state space, omega x, it's a discrete state space. Then the joint distribution of the observations and the latent states can be written as the distribution of the initial latent state. Then you have the transition distributions for the latent states. And then what's known as the emission distributions. The observation at time t only depends on the latent state at time t. And of course it has some parameters here. It depends essentially only on this quantity and on nothing else. Okay. So pi is the distribution of the initial state. A is the Markov transition matrix. Well, we assume that here it's the transpose of the Markov. It's transpose of a Markov matrix, of a stochastic matrix, because the columns are these transition probabilities, probability vectors. And then phi is the parameters of the associated emission distributions. So phi consists of k values, phi 1 to phi k. So phi k is just the emission distribution when the latent state is k. So latent state is from 1 to capital K. When the latent state is small k, then phi of small k is the parameters of the emission distribution for that. Okay. In terms of that, the latent states x can be integrated out to obtain the marginal likelihood as follows. So it's this quantity. I mean, I'm not going to derive this. It's essentially p. What this slide essentially says, you can essentially obtain the marginal likelihood, but this marginal likelihood is this product of t terms combined to t, which is probably not surprising because you have to evaluate it anyway. If you evaluate all the t observations. So P of yt is a diagonal matrix, and then you have 1 is a vector of 1s and so on. A is a stationary distribution. It's not terribly important what these quantities are, but the fact that you can obtain it is important. So we're interested in Bayesian inference. So give it a prior P0, the posterior is just in terms of the likelihood times the prior, which can be written in the form e to the minus u theta, where u theta is known as the potential function. So gradient-based MCMC depends on taking gradients on this potential function, which is what we'll talk about next. Okay. So essentially you need to calculate the gradient of u theta, which has these components. So there's a typo here. This should be a negative here. I think I probably made this typo. Anyway, the prior is not very important in this term. So basically the likelihood is the tricky part here. So of course you can explicitly calculate the gradient of the likelihood, but this is quite tricky because you have to take first of all sum of t terms, but that's more importantly, what is more important is the thing here. So you have to look at what happens after time t and what happens before time t. But anyway, so this is the point here is that you can actually do it if you want to, but it's expensive to do. So what happened is there was a paper in 2017 which proposed stochastic gradient MCMC for hidden Markov models. The stochastic gradient MCMC for IID observations has been around for longer. It became I think popular in 2013 by an ICML paper by Iwaite and Max Welling, who constructed what's known as stochastic gradient non-German dynamics. So stochastic gradient MCMC based on non-German dynamics, and then Ma et al. Extended this to hidden Markov models. So the way this works is as follows: you take your entire observation and you divide it into subchains. So what's a subchain? Well, you consider any tau, it's its time index, in 0 to t, or basically not 0 to t, but L plus 1 to t minus L. So L is what's known as the half width. So you look at what happens so you look at L observations after tau and not L observations before tau, and you call that your subchain. So the subchain is now of length 2L plus 1, and it's centered at tau because it says center is in this tau. And you define P of y tau as the product from tau minus L to tau plus L of these guys. And what you do is essentially you take your whole observation chain and you partition this into these subchains. So y tau 1 to y tau n, you divide it into these subchains. And using this, you construct gradient estimates. Then the gradient can be expressed as using these subchains as follows. So essentially now instead of having sum of t terms, you have sum of n terms, but then you have it, so it becomes sum of n terms, and then it looks like that again. So again, you care about what happens within the chunk, you care about what happens before the chunk, you care about what happens after the chunk. You look at this quantity, or not the chunk, the subchain, sorry. So what happens before and after that. I'll use the words chunk and subchain kind of interchangeably here. But unfortunately, calculating these quantities q and pi are expensive because pi again is what's happening before, so you have to pass through the entire chain before it. You can do that using a backward filter, and then you can calculate this using what's known as a forward filter again, but you have to again look at the whole chain from after the sub chain to the end of the series, so it's expensive. So these are approximated using buffers. So essentially the idea is you assume that the latent Markov chain mix is fast. So essentially if you are in at time t, you don't care about what happens after b steps after time basically t plus b, because you assume that the Markov chain has mixed fast enough. So essentially if you don't care about what happens too very much in the future and then very much in the past, because these are essentially independent. So that's the main assumption. Using these quantities you estimate these quantities q and pi using these buffers. Of course, these are no longer now unbiased estimates of q and pi, so q bar and pi bar are no longer unbiased estimates. However, there has been work showing how these estimates, basically how accurate these are as the buffer increases. There has been research on that. People have shown that essentially it mixes, if b is large and if the latent Markov chain is mixing fast enough, then you essentially don't need a very long, practically you don't need a very long buffer, and theoretically it essentially is exponential in terms of the buffer. It decreases exponentially fast as you increase the length of the buffer. So these results have been shown. Okay, so I talked about stochastic gradient. MCMC stochastic gradient estimates usually constructs an unbiased estimator of the stochastic of the gradient, which is it constructs an unbiased estimator. So far we don't have an unbiased estimator, but what we'll do here is, so here we have a sum of n terms. We replace q and pi by q bar and pi bar, and we'll do another approximation where instead of having all these n terms, so these can be also very large because t is large, and then t by 2l plus 1 can also be very large. So we don't want to take all of them, so we just do the random mini batch of size small m, which is m is much less than n, and this leads to an approximated gradient with the components, which is basically the important sampling essentially. So what's the probability that point m is in the subsample, and then you have these gradients as before. We have replaced q and pi by q bar and pi bar. Okay, so for example, if you choose these uniformly from 1 to n, 1 to the number of subchains, then the weights are just 1 by n. What we are going to do later is we are going to choose importance subsampling. We are going to give these importance weights, and we are going to talk about how also we choose these importance weights. Okay, so what about the performance of stochastic gradient MCMC? Well, it turns out that it's not surprising, but what happens is the variance of the stochastic gradient has a direct impact on the efficiency of the stochastic gradient MCMC, which means if you have variance, if you have a very accurate stochastic gradient, then you have a much better mixing Markov chain, and the Markov chain essentially does much better. The SG algorithm does much better. And if you have a very uncertain estimate of the stochastic gradient, that means a gradient estimated with high variance, then it does not do as well. So we talked about, I mentioned rare states. So when the latent Markov chain has some rare states, say omega rare, so remember that state space was 1 to k, it has some rare state, let's say state 1 is a rare state. Then what happens is that latent chain X is going to spend only a short amount of time in the rare states. If state 1 is a rare state, then you're going to have very few observations corresponding to state 1, latent state 1 in your chain, in your observations. So if you do uniform subsampling, what's going to happen is you're not going to pick many observations corresponding to the rare latent states. So essentially, observations corresponding to rare latent states are going to be absent or very rare in the mini batches, which essentially means that you're not going to really get much information about these rare latent states. And if you look at parameters associated with these rare latent states, for example, the emission parameters of these rare states or transition parameters to and from these rare states, because you don't observe the rare state very often, you're not going to have much information about the rare states, and you're essentially not going, you're going to have the gradient of components of theta associated with these latent states. The rare latent states are going to be going to have high variance. Sorry. Okay. So I'll just talk about importance of sampling. I'm just going to just formalize it a little bit slightly in a better way. So just write it in terms of weights. Suppose you have weights a1 to an, which sum to 1 and a positive, then an unbiased estimate of the gradient. This is just as before, where I've written instead of 1 by p of jm in the subsample, I just wrote it as the weights, which is this quantity. So the question is, how do you choose the important weights? Well, I'm going to change notation slightly. Earlier I talked about subchains. Here I'm going to talk about chunks. So basically C1 to Cm is just going to denote the sequential chunks. So chunks is basically the subchain was the observations in a subchain. So here the chunks is just going to denote the time indices. So C1 is just the time indices of the first subchain. Cn is just the time indices of the last subchain. That's all. And you'll see why I do that in the next slide. So how do we get this optimal, or how do we choose importance weights? Well, suppose somehow we quote unquote know the latent states. Well, no, suppose we know quote unquote the latent. Sorry, I'm not good with quotations, but the latent states the latent should be in quotes. Anyway, so suppose somehow we know what these latent states should be. Okay, we of course don't know it, but let's say we know it. If we did know it, then the log likelihood that we would be interested in would just be the log likelihood of, again, the transitions and the emissions, because now we know the transitions. We know what the xt's are, so we can calculate this guy, which has the gradient. So this is the sum of t equals 1 to capital T. The gradient, the gradient, the way we write it is we just divide this into these chunks. So we write it as t in chunks, and then the sum over the chunks. Write it like that. And as before, we do importance subsampling, where we have an unbiased estimator is just, we have some weights. We do importance subsampling as before. Okay. So as I mentioned, the variance of the stochastic gradient estimate has an important role to play. The lower the variance, the better you do. So what are the quote unquote optimal weights? Well, the way I define optimal is the weights that minimize the variance of the stochastic gradient. This can be calculated because we know what the stochastic gradient are, and we assume that we know the latent states. It's calculated like this. What's kind of important here, the numerator is important, the denominator is just a normalization term to make it sum to 1. Okay, so essentially what's important is these optimal weights depend on what's happening within the chunk. So this is for the chunk, so it depends on these emissions and the transitions within the chunk. Okay, but of course there are two problems here. There are two problems using this in practice. First of all, we don't know what the latent states are. We assume that we know it, but of course in practice we don't know it. And then the second problem is these weights depend on the current value of theta. So if we were doing SGLD and if we somehow knew what the latent states were, we would still have to calculate these weights fresh every time. So which means you have a weight that depends, which changes over time. And that's not a good thing. We don't want the weights to change over time. We want one set of weights, because otherwise it's not a practical algorithm. So we are going to do some heuristics we're going to use this idea to get some heuristics about how do you choose the weights. So, consider a latent state k, and let S of k be the indices of components of theta that are associated with k, and theta of sk are the associated components of theta. So basically theta of sk are all the components of theta that have to do anything with the state k. So for example, in terms of the transition matrix and emission parameters, this is the emission parameter for the kth state, and then all the transition parameters to and from the kth state. So these quantities. Okay. So basically this is just everything that has to do with state k. So a chunk Cn contains information about a component of this theta of sk only if there are observations corresponding to state k in the chunk. So if you let's take state 1. If you have observations corresponding to latent state 1 in the chunk, then you're going to get information about parameters associated with state 1. If you don't have any observation corresponding to state 1 in the chunk, you're not going to get any information about, for example, the emission parameters for state 1 or about transition parameters from state 1 because you don't have observed state 1. So we just assume that each occurrence of state k in a chunk provides one quote-unquote unit of information. This is kind of a heuristic observation. This is not really anything formal or theoretical as yet. We're still working on that, but it's just something that we kind of intuitively assume. Then the idea, of course, then the idea becomes what we should do is if you have a rare latent state, then we want to oversample chunks containing rare latent states for parameters associated with those rare states. So if state 1 is a rare state and we're interested in estimating the variance of the emission parameters for state 1, then we should oversample chunks that contain state 1. If you just do uniform subsampling, we are never going to pick state 1. We are never going to pick observations corresponding to state 1, and we are going to have very high variance for my stochastic gradient. Okay, so what we do it very heuristically. We just count the number of occurrences of the rare state. I select k rare is a rare state. We just count the number of occurrences of the rare state within each chunk. So here I know what the latent states are, so I can actually count this. Excuse me, I'll just drink some water. So we count the number of occurrences of the rare state within each chunk. Of course, the chunk is of length 2l plus 1, so it's between 0 and 2l plus 1. And we choose the weight to be proportional to this number of occurrences. So essentially it means that if the latent state has occurred more in a chunk, we just give the chunk a higher weight. And I add a small eta just to make the weight positive, because earlier I said the weight should be positive. I mean, the weight can be 0 as well, it's fine. But if 0 means it, we just never choose it. Okay. So, but of course, we don't know what the latent states are. These are unknown. So the way we approximate the latent states are as follows. So what we do is we just look at the observations y1 to yt, and we cluster these observations. So we have y1 to t, we cluster them into k clusters, c1 to zk, and let z of t be the cluster label for the tth observation. So basically zt is k equal to k means yt is generated from the latent state k. So we use these zt's, the clusters, as the cluster labels as proxies for the latent states. Okay. So how do we know which is the rare state? Well, if one cluster contains very few observations, we just assume that that's the rare state. So if cluster 1 is very small, and cluster 1 is only 1% of the total number of observations, everything else is larger, so we say that that's the rare state. So what we do is, as before, we just, instead of counting the number of occurrences of the latent states within a chunk, we consider the number of occurrences of the cluster labels within the chunk. So we count how many times does the cluster label k rare happen within a particular chunk. So remember, chunk is over time. So if you have a chunk over time, how many times do you have observations corresponding to these the rare states? Where of course we've used these as proxies. We use the cluster labels as proxies, and we do it as before. Okay. I'm going to have one numerical example. This is still ongoing work. We are still investigating these things more, but I just have one example where we have 4 latent states. So as follows. So we have 4 latent states, and state 4 is a rare state. So what happens is if you are in state 1, the columns are again the transitions. If you are in state 1, well, you have a 97% chance of staying in state 1, you have a 1% chance of going to other states. So state 4 is a rare state. So you have a 1% chance of going to state 4 from all 3 states, 1, 2, and 3. And if you are in state 4, you have a roughly 1/3 chance of going to the 3 different states, and then you have a 1% chance of staying in state 4. Okay. We let the emission distributions be normal mu k sigma square, where we have the emission means are separated, fairly well separated, -6, 3, 0, and 4. And then the variance is just half. And we simulate observations from this, where t is approximately, the length is approximately 150,000. Okay. Here's what the observations look like. So remember, there is a there is a cluster kind of at -6, there's a larger one at -3, there is something at 0, and then you have a very small thing at 4. So this is the rare state. Basically, you have a rare state here. It looks like that. Okay, and this is the final slide. I'm just going to talk about the example. I mean, this is work we're doing, so this is just one illustration of how this clustering based subsampling can help. So if you are doing import, so what I plot here is just I look at the STL iterations, and then I run it for like 3000 iterations. I look at it over time, and I just plot. So I have 4 emission means. I just plot the emission means. for uniform and clustering based subsampling. So for uniform subsampling, what happens is the uniform subsampling is basically not able to recognize that there is a cluster, or there are 4 states basically. It doesn't know that there is something going on at 4. But the clustering based subsampling eventually gets there. It kind of knows that there is something going on at 4. It kind of eventually moves to that point. But what the uniform subsampling is able to know that there is a state at -3, -6, and then there is something at -3. Unfortunately, the clustering based subsampling does not know this. It thinks that there is something at -4. It kind of thinks that there is something here at -4, and it kind of merges these two guys. It doesn't recognize that there is a bump here and there is a bump here. But we were interested in more interested in the latent state, the rare latent state. I'm sorry. So as far as in terms of the rare state, this is able to find out what the rare state is. So this is okay. And in simulation, we did observe that in these kind of things, sometimes the model is not able to clearly distinguish these two states. It sometimes kind of lumps these together. Sometimes it also lumps like these two guys together. But what's kind of more important is that we find out we can recognize this state, because in applications, and we're working on this, so in applications, this could be, for example, you have some heartbeat data or something, and you care about what happens in some rare event regimes. So we really care about these rare event states. Well, that's all for my talk. It's strange for me to give a talk like this sitting in my home, but thank you, and I hope just email me with any questions. In my email address here, yeah, it's deborshee.chen@edu. Thank you.